Our final plenary talk will be given by Dr. Aretha Teckentrup of the University of Edinburgh. Dr. Teckentrup is a lecturer in mathematics of data science at the University of Edinburgh. Her research interests span the fields of uncertainty quantification, Bayesian inference for computationally intensive forward models, multi-level sampling methods. She will be giving a talk today entitled The Best of Both Worlds, Blending Mathematical Models with Observational Data. Dr. Teckentrup, it's a pleasure to have you here. Take it away.
Okay, thank you very much, Stavros, and thanks also to the other people on the committee for giving me the opportunity to speak here. So what I want to talk about today is essentially data science, right? So blending, in particular blending, blending mathematical models with observational data. So as I said, the general topic is data science, particularly focus on combining mathematical models with observational data. So my plan for the talk is the following. So I'm going to kind of have three different parts. In the beginning, I wanted to just give a general overview of the area. So some topics in the mathematics of data science. So, I mean, data science is really a very broad area, and there's a lot of other areas that go into it as well, not just kind of mathematical problems. So there's also a lot about actually just collecting the data, cleaning the data, storing the data efficiently on the computer and things like that. So I'm not going to really be talking about anything like that. I'm just going to be talking about, let me just check the chat, no, okay. So I'm just going to be talking about kind of the mathematical aspects. So once you have the data and you want to process them, how do you do that? What methods and algorithms can you use in that case? Right? So that would be the first part. And then I wanted to discuss two particular examples that I'm working on at the moment. So there's one example in numerical weather prediction and another example which comes from geophysics. Right, so let me get started with the first part, just talking about data science a bit in general and what kind of problems we're interested in this area. So you might have heard the term that we are in the era of big data, right? So that means that in the last decades, there has really been an explosion in the amount of data that we have available. We do just have a lot of data available to us nowadays. There's several reasons for that. So one of them is the development of sensor technology, right? So just the technology that we have today to actually collect this data is a lot better than we had. In particular, in the last decades, this has really developed at a very fast pace. So if you think of collecting data in a lab environment or in hospitals, if you're collecting data in the context of medicine, or if you're out in the field, in field studies collecting data, you just are able to collect a lot more data, and also data that is just of much higher quality, just because the sensor technology has really developed in the last couple of years. Right, so that's one reason. Another reason is also the rapid growth of the web economy. So essentially all of the data that we're getting from our use of the internet nowadays. Right, so the social media sites, for example, like Instagram, that gives us a lot of data about how people travel, for example. Right, so everybody posts their travel pictures on Instagram. So that actually gives us a lot of data there, how humans travel and what kind of travel habits they have. There's also a lot of data coming from mobile phone technology. So from there, the data that you're collecting there, there's also a lot of data coming from there. Right. So in the end, what you often want to do is you want to make some decisions. So once you have that data, you typically want to process it somehow. And in the end, what people eventually want to do is they want to make some decision based on the available data. Right? So that means that you need tools to inform decisions, assess the risk associated with this decision, and then also formulate policies based on the evidence that you have. Right? So exactly what you want to do and exactly how you want to process the data depends on the context. So in different applications, you'll have different types of data and you'll be interested in doing different kinds of things. Right? So for example, in some application areas, For example, like the social sciences. So as I said, there's a lot of data coming from social media platforms such as Instagram. In these areas, you do really have a vast amount of data. So there's really a huge amount of data available nowadays. So it's coming from social media such as Instagram, or also from mobile phone technology. In that case, there's really huge amounts of data available. And the problem might actually be that you have too much data and you kind of need to reduce the size and kind of extract some of the useful data, because the data sets are really just too big to deal with. Okay. On the other hand, we do have some applications where, even though we nowadays do have more data, we still don't have that much data. So we still have sparse data, in the sense that we might have some data and it might be high quality data, but we don't have that much of it. Right? So if, for example, in engineering applications, if you think about petroleum engineering, so oil reservoir modeling and things like that, the data usually comes from measurements that you take by drilling wells. Right? So whenever you want to measure something that's going on in the subsurface, you have to drill a well, and then you get measurements from there. You don't really drill very many wells because each well is very expensive, and so you don't really have that much data, and you don't have that many measurements available. Right? Similarly, maybe in medicines, if you're collecting data from patients, again, you might not have that much data that is available to you. Right? So the amount of data that you have does depend on the application, and in some cases you really have huge data. In other cases, you don't have that much data. Right? At the same time, there's also the issue of mathematical models. So if we are on this side, again, where we have engineering and natural sciences applications, those are actually areas where we do have quite strong mathematical models of the processes that are going on. So again, if you think of petroleum engineering, what you would do is you model the flow of water and oil underground, and those processes are processes that are quite well understood from physics, right? You just have a flow in a porous medium, and so there's physical laws which tell us how those flows behave. And so in these areas, we typically have quite strong mathematical models of the processes as well as the data. Whereas on the other hand, in application areas such as the social sciences and technology, we actually sometimes we don't really have very strong models. Right? So if we go back to the Instagram data, for example, so that gives you information about people's travel habits, and that is something where you don't really have a good mathematical model. Right? So modeling human behavior and human preferences is very difficult. We don't really have a mathematical model for that, and so in that case, you don't have very strong models. So there are applications that, of course, sit in between as well. So I give you some examples where you do have a lot of data and not very strong models. It could be something in between where you have a lot of data and mathematical models, but these are generally kind of the two extremes that you should think of. Okay. And then what you want to do and what you want to do with the data and how you process the data is then very different in these two scenarios. So whether you're on this side or on that side. Okay. So if you are in an application area where you do have quite a strong mathematical model of the process that is going on and generating the data, and you do have some data available, you're typically interested in doing one of these three things. So you might want to do model calibration. Okay. So what that means is that you're tuning the parameters in the model from the data, right? So you're using the data to tune the parameters in the model. So for example, again, if you're modeling subsurface flow, then you do have these physical laws that tell you how the fluid flows underground. But in order to know, to then use the model, you would have to know exactly what the subsurface looks like. So whether you have a layer of sand or whether you have a layer of clay, and exactly where they are. So that is something that you typically don't know. And so these physical parameters that then appear in the models where you don't know the value precisely, you can then use the data to actually tune those parameters and calibrate your model to model the specific situation that you have. Okay. Another thing which is a bit related is filtering. So in the filtering context, you have some sequentially observed data, which means you're observing data over time. And then you also have a dynamical system that models your system of interest, and you're trying to blend them in the sense that you kind of want to combine them to give the best prediction. Right? So that is, for example, in applications in weather prediction, where we have our dynamical system, that is the mathematical model of how the temperature is going to behave. The mathematical model is not perfect, right? So there's typically some simplifications going on to make it tractable. And so the trajectory that you have from the mathematical model kind of diverges from the real world. And so you do get some observations of the real world, which are maybe here, and in filtering, you then kind of trying to push the trajectory of the dynamical system towards your real data. And so you're kind of trying to get that to blend together. There's also optimal control and optimization problems. So in that case, you have a model which has some control, so you can kind of steer your model to a desired state. So this is applications in aerodynamic design, for example. So you have your airplane and you want to design it so that you have kind of the best speed or whatever you want to have. And so then you can kind of steer the model towards having some desired state, which would come from the data. Okay. So these kind of things, usually the tools that you need are statistical inference, so Bayesian inference and high-dimensional sampling methods. Markov chain Monte Carlo is also very often used, and high-dimensional optimization problems. Right. On the other hand, if you if you have a very large amount of data, but you don't really have very strong mathematical models, what you would want to do is more in kind of this area. So one thing you might want to do is really just look at the data and say, what can the data tell me? So you really want to look at the data and try and extract information and extract features. So you're kind of asking, what patterns are there in the data? So that is, for example, in image processing in medicine or astrophysics. So then you're really just looking at the images that you have and try and extract features from it, right? So if you have some images, for example, in medical imaging, then you quite often want to know, is this, for example, a healthy brain or a non-healthy brain? Is there a tumor? And so you're really just interested in looking at the data and then getting that feature extracted, whether there is a tumor or not. Another thing that you might want to do is actually learn the model, right? So we do have a lot of data, but we don't really have a good model for the process that is generating the data. So you might actually want to use the data to learn that model, right? So that was what Des Hayem was talking about. Earlier today, you have some process, this function capital F, and you have some data value available on that function capital F, but you don't really know what it is, and so you want to use the data to learn that model. And so it's kind of doing regression on that function. Right. The other thing that's also important is software, right? So we do need to think about how we can actually implement these things once we have the methods. And so you have to think about scalable software as well, in particular if you're dealing in the if you're dealing with the large data context, you do have to think about how you can actually deal with that sort of data on the computers. And again, here's some keywords for things that some of you might have known. So neural networks and deep learning, again, that's what Des Hayem mentioned this morning as well. And then there's some of these software tools, TensorFlow and PyTorch, which again, some of you might have heard before. Right. So my research is really more on the left-hand side spectrum here. So in the area where we do have quite strong mathematical models for the processes that we're interested in, And we do have some data available as well. And we then want to combine the models and the data to get the best predictions or make the best decision that we can, right? So for whatever we want to do, we do want to make sure that we use all of the information that we are given to get the best answer. And so in addition to the mathematical models that we have, we do want to use that data that we are given as well. Right. So as I said, in the end, typically what you want to do is you want to process the data to enable some sort of decision making. And in the areas that I'm interested in, or in the setup that I'm interested in, what you have is usually some observed data. So it's usually partial data and noisy data. So there is some noise in the data, and partial means that you typically don't observe the whole process. So the process that you're interested in modeling is quite complicated, and you typically can only observe, say, some of the outputs, or you can only make some partial observations. So you do have some data, and then you want to combine that with the mathematical models in order to make your decision. Yeah. So what I'm interested in is then developing algorithms and tools that allow for efficient prediction and risk assessment by integrating real-world data with complex mathematical models. And in particular, in the context of risk assessment, so if you want to make a decision, you typically need to know how sure you are about any of the outcomes. So if you have to decide between different scenarios, you know, you have to be aware of which of the scenarios is most likely and what the different risks are associated to them. And in that case, you then really have to make sure that you also take into account any uncertainty that you have. So for example, since there is noise in our observed data, that is going to be some additional uncertainty in the sense that we don't really know if we can trust the data 100%, or if there is maybe some errors in the data as well. And there might also be some uncertainty in the sense that you are not, you have some incomplete knowledge about the physical system. So whether the physical model that you're using really captures everything that is going on in your system 100%. Right. So let me now talk about the first example. So the first example I wanted to talk about was numerical weather prediction. So in numerical weather prediction, we do have these two things. So we do have data and we do have our mathematical models. So we do have data from weather balloons, satellites, and also buoys. And then the model that we have is in the form of a partial differential equation that then governs the evolution of the state of the atmosphere, and that's going to be a PDE that depends on time and space. Right? And I mean, in numerical weather prediction, what you want to do is you want to predict the weather in the future, and to do that accurately, you really do need to do both, right? So you do need to use the observational data, and you do need to use the model that you have, right? So if you think about only using the data and not using the model, that is essentially saying, if I know what the weather is today, predict the weather tomorrow, but not using the mathematical model that we have, that's telling us how the weather evolves, right? So that is pretty much impossible. You can try and do it, but it might just be guesswork at that point. And similarly, if you want to use only the mathematical model and not use the data that you have, again, that would be impossible, because the data is what tells you what the weather is like now, right? So all the data that we're getting is telling me what exactly the pressure in the atmosphere is, 50 kilometers above Edinburgh, or whatever I need to know. If I don't know that, if I don't know what the weather is like right now, I'm not going to be able to use the model to predict the weather tomorrow, right? The weather tells me, the model tells me how to evolve it forward, but if I don't know where to start, then I'm not going to be able to evolve it forward. And so you really do need to both use the data and the model that you have. And so the way that you're combining the data and the model in this case is that you're using the data to update the initial conditions. right? So as I said, if I now want to predict the weather for tomorrow, what I would do is I would pick the initial condition for the weather depending on the data that I have, and then I would just run the model forward in time to get the weather tomorrow. And so we're using the data to update the initial conditions. And what I mean by sequentially update is that we do this every day, right? So every day we're getting new data. So the data that I have today is my initial condition today, and then I run it forward. Tomorrow I'm going to have new data. So then tomorrow that new data is going to be my initial condition, and so on, so that I initially, sequentially always update the initial conditions. Right. So the question is then, which initial condition should I pick, right? So how do we actually do this? So I said I'm now going to use the observational data that I have to choose the initial conditions for my model. Okay? But the problem is that the data is not complete, so I don't have the full data of everything that is going on in the atmosphere, right? That would require an infinite amount of data. So I only have a finite amount of data, so I only have partial data about there's some processes that I'm maybe not observing, and there's some time and space locations where I'm not observing things. So I only have partial data, and so that means that there's really many possible initial conditions that fit with my observed data. In particular, there's
I believe we have a problem with the connection. Please bear with us. We're trying to resolve this.
okay, I'm not sure how long I was gone. Sorry, I had some problems. My internet stopped working.
I think he was only frozen for a short amount of time.
Okay. Just okay, so I'll just start with this slide again. I think that should be okay, right? So what we're doing then is we're not just choosing one initial condition because we can't be sure what the initial condition is. And so we choose a whole ensemble of initial conditions. So we choose a large number n of initial conditions that are consistent with my observed data. And then for each of those initial conditions, the model forward to get what the weather is tomorrow. And then to make predictions, I just use summary statistics of the ensembles that I've computed, right? So what that means is that we get this whole ensemble of predictions, right? So I don't just run, so every globe here corresponds to the weather tomorrow with one certain initial condition. So you get this whole ensemble of possible future predictions for tomorrow. And if I then, for example, want to know what is the what is going to be the temperature in Edinburgh at noon tomorrow, I would then look at all of the possible values that I get for that quantity, and then take the average to see what I can expect. Right? And this is also how you get your percentages in the these weather predictions. right? So this morning in Edinburgh, it was raining very heavily. So there was an 80% chance of precipitation, whereas now in the afternoon it's cleared up and you only had a 10% chance of precipitation. And again, how they compute this is by looking at this ensemble of predictions that they have. If 80% of these say it's going to rain, then they say there's an 80% chance of rain. And if only 10% of these simulations show rain, then they put a 10% chance of rain. So the problem with this is that it is practically and numerically very difficult to do. So this is something that is extremely time consuming and extremely expensive to do. And the reason for that is that you have to run a very large number of simulations. So you have to have a large number n of initial conditions in order to make sure that you've covered all of the possible scenarios. And each of these simulations individually is also very expensive, right? So what you have to do for each individual simulation is predict the whole weather tomorrow. So individually, that is also going to be quite expensive to do because you have to solve a very complicated PDE on quite a large spatial scale, right? So you would typically have to do the whole of Europe or at least the whole of the UK. And so that is quite time consuming to do. So it makes sense intuitively. You can also show that mathematically. So mathematically, what you're doing is you're doing sample averaging or Monte Carlo estimates. So in these ensemble methods, what you do is you just have this ensemble estimate, right? So if you want to predict some quantity phi, which again could be the weather in Edinburgh at noon tomorrow, for example, what you would do is you would run your n simulations. For each of those n simulations, you would then get a certain prediction for that quantity. And then you just take the average of that in order to predict what you think is the most likely outcome tomorrow. Right? You also have the extra approximation coming in from having to solve things numerically, right? So the PDEs that govern this weather are too complicated to solve analytically. So you have to solve them numerically with some step size h. So you also have this h approximation coming in here. Yeah. And you can then look at the mean square error of this estimator, right? So you can look at your estimator, so the thing that you are computing, and look how well it approximates what you really want to approximate, right? So you want to predict your quantity phi, and just look at the mean square error. And then as usual, that splits into the variance plus the bias squared. Okay? And then you can use some properties of your ensembles here to show that it particularly has this form here. So you get one error which depends on the ensemble size n, and another error which depends on your numerical discretization error, so the error between the true PDE solution and the numerical PDE solution that you have to do with some step size h. Right? So you get these this split into the two different errors, and you can see if you want to make the mean square error small, you have to make both of these individual terms small. And so you have to choose a large number of samples, and you have to run very accurate simulations, right? So you have to solve the PDE accurately you have to solve the PDE accurately with a fine step size h, right? So this can very quickly become very expensive, and there is a lot of research going on now trying to reduce the computational cost of this, and this same problem pops up in a lot of other application areas as well, where the problem is just that you are dealing with a system, in this case the PDEs, that govern the numerical weather, that are just extremely time consuming to deal with. Right. So let me now go on to the second application. So the second application is in geophysics, and particularly in the modeling of subsurface flow. So again, we have data as well as a mathematical model. In this case, the data is data that we collect from drilling wells and taking measurements. So in this case, we really typically don't have a lot of data because drilling wells is expensive. And the model that we have is again given by a partial differential equation, and it is the PDE that just governs the flow of water underground. So in that case, that is just given by Darcy's law plus conservation of mass. So Darcy's law just tells you that the water is going to flow in the direction of the pressure gradient. So it's going to flow from areas with high pressure to areas with low pressure. If you combine these two things together, you get this elliptic PDE that you have here, where the P is now the pressure head of the water, the G is any sources or sinks. So if you have some water coming in somewhere, so if there's a well essentially, then you have some source and sinks terms. And the coefficient that you have here is K is the permeability. It's also called the conductivity. So this is just a property of the rock that is in the area that you're modeling in the subsurface. And it's a measure of how well water flows through that type of rock. So rocks which have a high permeability, water flows through quite quickly, and rocks that have a low permeability, water flows through quite slowly. Okay. So this has a couple of interesting applications. So for example, in nuclear waste disposal and carbon storage underground. So both of those are things where you store something and bury it underground, and it's very important to quantify the risk of any leaks happening, because if something leaks, then it can be transported by the groundwater back into the human environment, and so you really have to quantify the risk of that happening. Right. And again, it's very important that you use both the model and the data, because you can't solve this problem just with the data or just with the model, so you really do have to use both. So in particular, you can't run any simulations with the PDE model if you don't know what the permeability is. So in this case, the data is going to tell us what this parameter K in the model actually is. Similarly, you can't do anything with only the data and not using the model, but because in this case, the data is really very sparse, it doesn't give you that much information. And so just using the data to do anything is not really going to work. Right? So how are we combining the data and the model in this case? So in this case, we are actually inferring the coefficient in our model, right? So we have this model that we know governs the flow of water underground, but we don't really know what this permeability K is, right? So that depends on what kind of rock you have, and you might not be sure exactly what type of rock you have. And so that is information that's going to come from the data, right? So by drilling into the wells and looking at what kind of rocks you have and how many layers you have and where the different layers are, that is then going to give you the information that you need on K. Right? So as I said, the permeability K depends on what kind of rocks you have. So typical configurations of the subsurface might look something like this, where you have different layers and then different types of rock, right? And typically you don't really know exactly where the different layers are without having any data. So that's where the data comes in, right? So if you ask a geologist, they might be able to tell you something. So they might, for example, be able to tell you, I think there's a layer of sand and then some clay and loam, but they wouldn't be able to tell you exactly where the different layers are. And so you need to collect some data in order to figure that out. Yeah. And then here it's just an illustration of the spread of the pollutants. So if you do bury some nuclear waste or CO2 underground and it does leak, then it will be kind of spread through the subsurface in a kind of diffusive manner, and it could potentially then re-enter the human environment, and then you have to model how this behaves and how this spreads in order to assess the risk associated with an event like that. Right. So let us now consider, for example, this problem here. So the task of assessing the risk of a pollutant re-entering the human environment that is related to this problem here of predicting the outflow of water through parts of the boundary of an aquifer. So you have your aquifer, which is the kind of part of the subsurface that you want to model. And we're now interested in predicting how much water flows out through part of the boundary. So this is a particular setup where I'm just working on the unit square, which is why I have the 0 and the 1. This is the flow of water, and so then I'm interested in how much water flows out through this boundary. So I'm just integrating over this boundary and looking at how much water flows out. Okay. So the way that you can do this is again using Bayesian inference. So as I said, the problem is that we don't really know what K is. So what you do is you assign a probability distribution to the permeability K that is consistent with the observed data that you have. So typically you have some observed data on K itself and also on the related solution P. You typically also have some expert knowledge, so things like knowing what type of rocks there are and maybe how many layers you are expecting, things like that, which the geologist would tell you, but then also goes into this probability distribution that you can then do usually using Bayesian statistics. This expert knowledge would go into the prior distribution there. You then sample from this distribution on K using, for example, Markov chain Monte Carlo methods, such as Metropolis Hastings. Then for each possible value of K, you then compute your outflow Q, and then in the end you again use an ensemble average, right? So this is again an ensemble method where you pick different realizations of K, which are consistent with the information that you have. And then for each K, you compute your quantity of interest Q that you're interested in. And in the end, you then take ensemble averages to predict what your estimate is. Again, this is something that very quickly becomes computationally infeasible. So if you just use standard Markov chain Monte Carlo methods that are known today, this quickly becomes very, very time consuming to do, again, because you're dealing with a very big and complicated model. So computing this outflow Q for each value of K is something that is very time consuming to do. And then if you have to do this many times, then that very quickly builds up, right? So here's an example where I'm now looking at the relative accuracy. So I'm computing my quantity of interest Q with a relative accuracy epsilon, and I'm looking at the time that it takes me to compute the solution. With the standard methods that are that have been known for decades, you get the cost in the blue line, and this red line is a new method that we developed. So in this case, we developed a new method which you can see reduces the cost, and in particular, it reduces the cost by a really large factor. So if you're looking at the last data point here, so the one which is the most accurate, where you're looking at an accuracy of around 5%. So you're looking at a relative accuracy of about 5%. So you have about one significant figure correct in your computed output. In that case, the standard method actually took 140 hours, which is almost a week, whereas the method that we developed finished it in almost 5 hours, right? So that is really a huge benefit that you can get there. And this is not even a very complicated problem. So if you really want to do large-scale applications, then the standard methods that are out there, such as this blue line, often very quickly become computationally feasible. And so there is really a need to develop new methods. Okay? So that was really all I wanted to say. So in the context of big data and data science, I think there are many new interesting challenges for mathematicians to tackle. And in particular, there is really a need for efficient algorithms that can cope with both the complex real-world systems that you're dealing with, so the PDEs that come from weather prediction or subsurface flow modeling, and also deal at the same time with data, and in particular data from different sources. All right, so thank you for your attention, and I think I ran a bit over time, so I apologize for that, but I'm happy to answer questions.
Thank you, Dr. Teckentrup, for providing a very interesting presentation. There are a few questions submitted by the audience. So the first one is, some of the reasons for a lack of mathematical models in some industries is the issue of legacy systems. Is there a way you can have the best of both worlds?
I'm not sure I understand the question. I mean, if there is no module, I mean, if you...
We could take this offline, so I could proceed to the next question. Have you found that sometimes when data suddenly becomes available from a prior small set, the models previously used are shown to be less helpful?
I personally haven't, but I'm 99% sure that has happened. Yeah, I mean, the thing is, you can't really validate models, or it's difficult to validate models if you don't have any data, right? So if there is an application where you previously really didn't have any data, then it was very difficult to really validate that model on anything. So I'm pretty sure that would have happened.
Okay, there is also one more question. Do you envisage recruiting quantum computing machinery in the future to reduce computational time?
Sorry, can you repeat the question?
Yes, do you envisage recruiting quantum computing machinery in the future to reduce computational time?
Yeah, I think, I mean, I really don't have a good feeling for the time scale at which this is going to happen. But I do think that quantum computing is getting more important, and there are people looking at it. I don't know that much about it, but I do think that in the future it will be used to reduce computational costs. But as I said, I'm really unsure about the time scale at which this will be possible.
Okay, and I have also a final question, which concerns numerical weather prediction and relates to this last question that we had. So due to the sensitivity of the atomisable initial conditions that you mentioned on the state response variables, I understand that uncertainty is accounted for by formulating the problem in a stochastic setting, therefore quantifying, for instance, the mean square error. And now, depending on the number of random variables, Monte Carlo simulations can be computationally expensive. And when combined with small discretization steps for numerical schemes, could be prohibitively expensive for some scenarios. So the question is really, how do you deal with this? And if there are any state-of-the-art approximation methods or surrogate modeling techniques that could be used to solve this problem? Okay,
yeah. So, I mean, there's different ways in which you can go about it. So one way is what I skipped over here. So there's these things called multi-level methods. If you're interested in that, you can look at multi-level Monte Carlo. So they are really developed with this in mind, doing Monte Carlo simulations for very expensive models. Okay. So essentially what that does is it kind of works with simulations which have a varying accuracy. So you don't do everything with a fine mesh size. You do a lot of things with a coarse mesh size and then kind of try and work with that. Okay. So that's one way. Another way is also going to quasi Monte Carlo methods. Right? So what quasi Monte Carlo methods do is they give you a clever way of actually choosing these initial ensembles, right? So in Monte Carlo, you just choose them randomly. So you put a probability distribution on your initial conditions, and then you sample from that IID, right? So you just have randomly chosen initial conditions. In quasi Monte Carlo, what you do is you don't choose them randomly, but you actually try and choose these initial conditions better. So you're trying to choose kind of the ones which give you the most information. So that's another thing that you can do.
Thank you very much. And I believe we have one more question. If you're familiar about missing data, and if so, how do you think it can help tackle these problems?
I don't really know anything about missing data. So I'm not sure.
That's okay. Sorry, there's one more question. Do you use parameter estimations for your parameters? Is it possible for others to test your models of your data?
So the first question was, do I use parameter estimation?
Parameter estimations for your parameters.
I mean, in this second example with the subsurface flow, the goal is to partly estimate the parameters. And so it's the parameter k that is unknown. So you do estimate the parameters in that sense.
Okay, and the second component is whether it's possible for others to test their models of your data. I suppose it means if the data are accessible for use on other models.
Yeah, I mean, I don't have, I haven't produced any data personally. I mean, we either use synthetic data, so running simulations with this model to produce a set of synthetic data, or I mean, there is some data that is also publicly available. So in the case of the nuclear waste disposal, there is a test plant in New Mexico. It's called WIPP, WIPP, the Waste Isolation Pilot Plant. And in that case, there is actually publicly available data there, which gives you data of the permeability and the pressure.
That's great. I think this completes the questions. So thank you very much for this interesting presentation.